My name is Emma Goldsmith, and my project is Modeling Hawking Radiation through Analog Black Holes in Nonlinear Wave Propagation. Black holes are famous for pulling everything in, even light. But according to Stephen Hawking, they also glow very faintly. That glow, Hawking radiation, is so tiny that no telescope on Earth can see it directly, as it is emitted as black holes dissolve. So I decided to ask a question. Can a small wave tank help us understand black holes better, and can it help us better model the mysterious workings of Hawking radiation and black hole death? Instead of trying to observe a real black hole, physicists have built analog black holes in the lab, systems that follow the same math but use things like water waves or light pulses. In my project, I turned a shallow water channel with an obstacle into a kind of tabletop black hole. It follows the similar processes of black holes, making it possible to observe and model their complex workings, such as Hawking radiation. In my project, water flows one way and waves try to travel against the flow. If the flow gets fast enough, there's a point where waves can't escape upstream anymore. That point acts like a black hole horizon, the point of no return in a black hole. What's special about my experiment is that I focused on nonlinear waves, waves strong enough that they don't behave like perfect tiny ripples. Most simple models treat the waves as small and linear, but I wanted to know, what really happens at the horizon when the waves are bigger and start to misbehave with nonlinearities? I wanted to know if we still get the kind of blocking and mode conversion that analog black holes and Hawking radiation rely on. To test this, I built a wave tank with a fixed obstacle in the middle and pumped water over it. I generated waves downstream and filmed the surface with a high-speed camera. Although I couldn't cheaply create nonlinear waves in a school-friendly setup, I combated this by specifically designing my obstacle with the generation of nonlinear waves in mind, and using a tank with a relatively narrow channel. This allowed me to generate nonlinear waves without extremely high speed pumps. This video demonstrates my setup with the pump speed flowing water over the obstacle, creating nonlinear waves. Later, I analyzed the video frame by frame and tracked the surface height at 3 locations. Point 1, which is upstream near the pump side. Point 2, which is right over the obstacle, where the flow is the fastest, and the differences are the greatest. Point 3 is far downstream, where the waves are still flowing, but less so. From the flow speed and water depth, I calculated the Froude number. This compares the water speed to wave speed. When the Froude number is about 1 or greater, waves can't travel upstream anymore. At point 2, I found Froude numbers greater than 1. That's where my analog horizon occurs. This is known as also the blocking point. When I looked at this what the surface waves was actually doing at each point, the wave behavior changed dramatically. Upstream at point 1, near the pump, the surface is much calmer. The height variations are smaller, and there is very little strong wave activity from the horizon that makes it into this region. In other words, the horizon really is blocking most of the incoming wave energy traveling upstream. You can see the varying frequencies of the different wave heights. They're spread out over about 0.4 inches and are fairly normal following the wave peaks and the lowest points. Right at the horizon, point 2, the waves become nonlinear and don't behave like we expected. The height versus time plot becomes more jagged and irregular. The data spreads out over a much larger range of heights, and the frequency is far more random. This means that the surface is being pushed much higher than the lower downstream areas and the upstream areas. This is a sign of nonlinear amplification and distortion, exactly where the flow becomes critical. The flow also varies over roughly an inch, showing that it doesn't behave as much as we expected like the other waves near the pump upstream. It's also far less regular, so it proves that it's not behaving like we expect. Downstream, the waves are relatively regular, similar to upstream. If you plot height versus time, you get a fairly clean repeating pattern. The heights are narrow and the surface stays typically one level with modest ripples, fluctuating less than half an inch. This demonstrates that it behaves like we expect, much like at point 1. With these points, in combination with point 2, we can see the mode conversion and the blocking point that the analog horizon creates. This preliminary data models Hawking radiation and shows that my current setup displays an analog black hole horizon. My next steps with this project include running more trials with varying wave types and pump speeds in different intervals to compare how they might model Hawking radiation better or in different ways. Furthermore, I also plan to conduct FFT analysis with my current and future data to better analyze how my setup compares to how we believe Hawking radiation actually behaves. Lastly, scientists around the world are using analog black holes with water, light, and even ultra-cold gases to test ideas about horizons and Hawking radiation. Those experiments have already given evidence that Hawking's mechanism of Hawking radiation is real and it can be modeled with these systems. My project fits into that line of work, but at a different scale. Instead of using a huge lab, I'm exploring how far we can push a simple school-sized wave tank to model Hawking radiation. By focusing on nonlinear waves and carefully measuring where the horizon forms, I'm adding data on what really happens at the surface of an analog black hole when the waves are not perfectly gentle and when they are nonlinear. My mission with this project is twofold. First, to test whether a small, classroom-friendly setup can still capture the key horizon physics behind Hawking radiation without needing exotic equipment. Second, it's to see how important nonlinear effects are at that horizon, and if they really do model Hawking radiation better than their linear partners. The impact is that if we can reliably create and measure analog horizons with nonlinear waves in a simple tank, teachers, students, and researchers can explore ideas about black holes and quantum fields in a hands-on way. This helps bridge the gap between abstract theory and experiments that students can actually see and run for themselves. In other words, I'm trying to turn something usually reserved for cutting-edge research laboratories into something that you can do in almost any high school lab, while still telling us something new about horizons and how Hawking radiation actually behaves. Thank you so much.